Okay, so in the junior cert for higher level, we learned how to formally prove, this was 5 theorems. There's 3 extra ones we have to prove for higher level in the leaving cert. So here they are. Right, the first one, if 3 parallel lines cut equal segments of some transversal line, they will cut equal segments of any other transversal. So what I mean by that is, if we have 3 parallel lines and I draw some transversal, if you look at the red line, and that red line is cut into equal segments. So one segment will be from here to here, the other segment will be here to here. And if those segments are equal, okay, so if the length AB is the same as the length BC, well then if I draw another transversal, well then these 2 segments should be equal also. Okay, but we need to prove that. We know it's true because we've learned that in second year. Okay, but we have to prove it. So here's how we do it. Well, what are we given first? We're given the line L, M and N, and they're parallel to each other. We're also given the transversal T, which cuts L, M and N at A, B and C like I've drawn. We're also given the transversal K, which cuts L, M and N at points D, E and F. Right, so what do I want to prove? Well, I said already, I want to prove that the distance, or the length of DE is the same as the length of EF. Basically that this transversal cuts that line, these 3 parallel lines cuts the blue transversal into equal segments. Right, it's construction. So what I'm going to do is I'm going to draw a line crossing A, so crossing this point here. I'm going to draw a line parallel to the blue transversal. So there it is. And I'll label these points F, so the A, B, C, D, E, F will go G, E. And then I'm going to draw another transversal parallel, cutting E, parallel to the red transversal. So here. So that's E, and this will be F, and this will be G. So for my construction, I can say I will draw the line, AE, which is parallel to DF or DE, whichever, and I'll draw the line EG, which is parallel to AB or AC, whichever I want. Okay. Now, what do I want to prove here? Okay. Well, if I could prove that this triangle here is congruent to this triangle here, right, then I would show that line AG is the same length as line GE, and seen as AG, this green line here that I drew, is actually parallel to this line, well that would also prove then that DE is the same length as as EF. Okay, I think I said parallel over here, but it shouldn't be. I'll start that again. So if I could show that AG is the same length, I think I said parallel for some reason, if I could prove that AG is the same length as GE, then by default I would show that DE is the same length as EF. Why? Well, because they're parallel lines. Okay, so let's see if I can do that. Try to tidy this up a bit. Getting rid of anything I don't want. Try that again. Okay. Right, so I'm going to prove that triangle, doing black I suppose would be better, triangle ABG and triangle GFE are congruent. So let's see if I can prove that they're congruent. Well, first of all, I can see that this angle here equals this angle here. See, because they're opposite angles. So I'll say that angle BGA equals angle FGE. And why is that? Because they're opposite angles. Okay, so we have an angle. Right. I can also say that line, do it in black. I can say that line AB equals line EF. And why is that? Okay, so I'm basically saying this here is the same as this here. Well, that's true because AB, so from here to here, is the same as BC, just from here to here. And those are parallel, so just try to highlight it for you now. So here to here is the same as here to here. And then E to F is also the same because that green line is parallel to the red one. So it has to be the same. So let's say I'll say AB equals EF, and why is that? Because I'll say it's assumed and it's parallel transversals. And lastly now, I can say that this angle here is the same. I probably should do it a different colour though. Okay, I'll do it in a blue colour. So I can say that this angle here is the same as this angle here. So I will say BAG, so angle BAG equals angle GEF. Angle GEF. And why is that? Well, because they're alternate angles. Right, so now I have a side, an angle, and I also have another angle. So therefore I know that triangle ABF and triangle GFE are congruent. So if these are congruent, I'll draw it. So if that is congruent to that, well then this line here has to be the same as this line here. But more importantly for us, this line here, AG, must be the same as this line here, GE. Right? So I can say, therefore, AG equals GE. So say again, this line here is the same as this line here. Right. Well, if that's the case, and that line is parallel to this line, well then wouldn't it be safe to say that the distance from DE to EF is the same? Okay, so I can say then, therefore DE equals EF. So DE equals EF. Okay, so the next proof is we have, it's kind of like the last one actually, and we're using our knowledge from the last one to prove this. So it says let ABC be a triangle, so we have our triangle, and if a line L is parallel to BC, so here's our line L, and cuts AB, so cuts here at X, in the ratio ST, so it means if this is S big and that is T big, then over here we'll have the same ratio. Okay, and just going to give you a little example in this. Again, we would have known it from junior cert. Let's say we have a triangle, it's cut like that, and this is, we'll say 2, and this is 4, and this is 3. Well, what's this? Well, think about it. This bit here is twice that bit, so this bit here should be twice that bit, so that should be 6. And what we really mean though is, if we were looking at ratios, 2 over 4 equals 3 over X, and if we look at the ratios there, if we multiplied, well, let's say we cross multiply it, we get 2x equals 12, so x equals 6, so that's 6. Okay? But the ratio really is 2 is to 4, so this bit, or 3 is to 6, which is this bit, but these are actually the same ratios because one is twice the other, so the ratio is actually 1 is to 2. Okay, so the ratio works for both, same ratios. So likewise I want to prove that the relationship, I suppose, between this length and this length is the same as the relationship between this length and this length. Okay, so what we're given the triangle ABC, the line L, okay, cuts an XY, and it's parallel to BC, which cuts AB in the ratio ST. So we'll go ST. And what do I want to prove? I want to prove that AY, so here, is in the same ratio. Okay, so also the same ratio ST. Okay, so what do we do? Okay, well, to make a construction, we'll divide AX into S equal parts. Okay, so many equal parts. And we'll also divide XB into so many parts, and we'll call that T equal parts. Okay, so I'm just going to get rid of this S and T for the meantime. Okay, right, so I'm going to divide this bit here into S equal parts, so many equal parts. I'm going to divide this XB into so many parts again, T equal parts. So here's what I do. First of all, I'm going to divide the top one. Okay, bear with me with this. 2, 1. So do a 3 for parts. Okay. And I'm just going to highlight this. the distance between here and here is actually the same as the distance between here and here and here and here, okay? So that's clear. But I'm going to call this K. Alright. And how many parts did I divide this into? I know it's 3, but I divided it into S equal parts. So from A to X is S K. Right. So that's all SK. I'm going to do the same now to XB. Divide it up and divide it into T equal parts. Okay, and again, the distance from here to here is K, and there's T amount of those K's, so this here is T multiplied by K. Alright, okay, now let's look over at this side here. Okay. Highlighting the distance from here to here. Right. Let's call that, it's definitely not the same size as this. Okay, so we can't call it K. How about I call it P? Right. Well, if this side here is S multiplied by K, well then surely this side here is S multiplied by P. And down here, and this is also P, this length here, and could I call this TP? Right, so here's my proof. Okay, and I'm going to refer back to my proof of the light. So according to proof, it's proof 11 is the last one we did. I should have said that most of the time. So according to proof 11, parallel lines cut off segments of equal length along AC. Okay, so what I mean by that is the bits I've highlighted in yellow here. That and that, okay, and that. They're all equal in length. Right. So I'll say that, oops, should I call it P? So let P be the length of each of those segments. Okay, so AY, which is this bit here, so the line AY equals S times P, and the line YC equals T times P. So YC equals T times P. So therefore, AY is to YC. Okay, so if I was to put them in a ratio, therefore equals SP is to TP, and if I divide by P on both sides, I will get S is to P. So I can say at the end, therefore AY is YC equal S and T. Sorry, not P. T. Okay. Okay, so the last construction. Right, so this is theorem 13. If two triangles ABC and DEF are similar, then their sides are proportional in order. So, for example, okay, let's just take, let's say this triangle was 4, 5 and 3, and this side was 2. Now let's compare these sides. This side is 4, this side is 2, there's corresponding sides, and they have a ratio of 4:2, which really is 2:1. So that means every other side should have the same ratio. So that means this side here and this side here should have the same ratio. So if that's 5, then this should be half that, which is 2.5. And likewise, if this is 3, then this should be 1.5, half that, because this is the ratio. 1 is half 2. Okay. We know that because we've seen it at junior cert level, but now we need to prove it. So that's what this here means, really. The ratio of the lines AB to DE, so if you look down the triangles AB, DE, so the relationship of those is going to be the same as the relationship between BC and EF, and the relationship between AC and DF. So AC and DF. Okay, so they're going to have the same ratios. So, given similar triangles ABC and DEF, to prove that the length of AB over DE equals the length of BC over EF equals the length of AC over DF. Construction. Right, what I'm going to do is, use a green pen, I'm going to draw line XY on triangle ABC so that triangle AXY is congruent to triangle DEF. What I mean by that is I'm going to draw a line here. This here will be X, this here will be Y. Now, this triangle here, the AXY, is congruent or the same as this triangle here, DEF. And that was my aim all along. Right. So now my proof. And I'll be referring back to theorem 12, which is the one we just done previously up here, to prove this. Because if you look here, it's to do with dividing triangles into ratios. Well, here's similar, okay? Because now I can almost forget about this triangle for a second. I can look at the ratio between AX and XB, and the ratio between AY and YC, and I can say that let me say AX over AB is equal to AY over AC. But have a look at AX. That's here. Sure, that's the same size as this. We made sure it was the same because we drew it. So I can say, but this is from AX, the distance from A to X is the same as the distance from D to E, and the distance from A to Y is the same as the distance from D to F. So therefore, the distance from D to E over the distance from A to B equals the distance from D to F over the distance from A to C. Okay. And then similarly, I can say the distance from E to F over E to C is the same as df over AC. Okay, so basically I'm saying also the distance from here to here and here to here, the ratio of that is the same as the ratio from here to here and here to here. Okay, so I can say then confidently that dE over AB equals dF over AC equals EF over BC. And I wanted this up here, so let's just have a look. Okay, which is the exact same as mine, except they have the numerator and the denominator is different to mine, so I can easily change that, that's no big deal. So I can say, what way did they have it? A, B, D, E, yeah. B, D, E equals BC, yeah, so it's this one. So BC, EF, and then this one, AC, DF. So there we go. Okay, so I know how to prove that. Yeah, thanks.